Hi there. So now we're going to talk about actually two sections at the same time. We're going to talk about some interpretations of the definite integral. Okay, so the first thing we need to do is recall that when you take the definite integral from a to b of some function, what we're doing is we're taking the limit as n goes to infinity of the sum of each of the areas of the rectangles. Okay, recall what we do is we subdivide that interval into n different rectangles. We find the area of each of the rectangles, and then we let the number of rectangles go to infinity. By definition, this is our definite integral. Recall also that since we're multiplying function values, that when we're below the x-axis, we're going to get a negative value. Okay? So right now what we want to do is take, like what we did with interpreting derivatives, we want to interpret our definite integrals. So what I want to do is point out that when we're computing a definite integral, we're actually multiplying two different values. We're multiplying our function value by this change in x value, whatever the length of each of those rectangles are. So if we want to talk about units, which is the thing that we focused on when we were discussing derivatives, when we want to talk about units, essentially what we're doing is we're taking the product of whatever the units for our function value are, along with whatever the units for our x value are. Okay, so the units of measurement when we talk about our definite integral are the products of the unit of measurement for our function value along with the unit of measurement for our x value. So I want to go back to a familiar one. You may recall that at the beginning we saw that when we had our position function, which we call s of t, when we take the derivative of the position function, we get our velocity function. Why? Because, okay, maybe this is in feet and this is in seconds. When you take the derivative, that's the slope. It's the change in distance over change in time. It's feet per second, which is exactly what the units of measurement are for our velocity function. So if we turn that around and say to ourselves, well, what's the antiderivative or the definite integral? If we want to talk about two values of our velocity function, we know that we're going to get back to our position function. But let's actually put this in terms of units, okay? This is in feet per second. What are the units of our time? Those are seconds. Notice we cancel out. And when we take the definite integral, we're going to get back to our feet, okay? Just as we would expect. So when we talk about the definite integral of our velocity function from a to b, what we're talking about is precisely the change in distance from time a to time b, okay? So this leads us to say the following. If some function f of t is a rate of change of a quantity, then the total change in quantity from t equals a to t equals b is the definite integral from a to b of the function. Okay, that gives us the groundwork from which we're going to proceed. Excuse me 1 second. Sorry about that. I just had to be sure that the microphone was plugged in. Alrighty, so what I want to do now is play with some examples so you guys can actually see this put into motion here. Okay? Alright, so for example, what if I want us to interpret the definite integral from 0 to 90 of capital C of t dt. And I'm going to tell you that C of t is the cost per day to heat a home. And we're going to say that the cost is in dollars. Okay? And we'll say that T is measured in days. And let's further suppose that T equals 0 corresponds to, I don't know, let's say January 1st of 2020. So how would we interpret this definite integral? Again, I always go back to units because I think that gives us a really good starting place. Okay, what are the units for C of t? That's the cost, or the dollars per day. T is measured in days. So again, those are going to cancel. So we're left with cost. Well, what is this the cost of? It's the cost to heat your home in the first 90 days of 2020. All right, let's do another interpretation. I'd love to stop and ask, does anyone have any questions? But I hope it's clear so far. All right, so what about this one then? What if I tell you that pollution is removed from a lake on day T at a rate of F of T kilograms per day? Okay? So, first, let's explain the meaning of F of 12 equals 500. Okay? So notice, what are we looking at? This 12 is the days. Okay? So, doesn't this say that on day 12, well, what is this 500? They're removing 500 kilograms of pollution per day. All right, follow-up question. Let me just put it over here. What if I then say that, let's look at the integral from 5 to 15 of f of t dt, and that's equal to 4,000. Okay? So the first thing I want us to do is talk about what are the units of 5, the units of 15, and the units of 4,000. Okay? Well, remember, these are our t values. So what are we looking at? 5 is days, 15 is in days. And what is the definite integral? Well, remember, it's kilograms per day. That's the units of our f of t. The units of t are days. So what this says is between days 5 and 15, 4,000 kilograms of pollution have been removed. All right. So let us go through another example here. Suppose I tell you that a forest fire covers 2,000 acres initially, so at acres at time 0. And we are also told that the fire is growing at a rate of 8 times the square root of t acres per hour. And I'm going to further say that T is time in hours. What I want us to answer is as follows. How many acres are covered 1 day later? All right. Well, notice we want to know the number of acres. What we're given is the rate. And again, how do you undo the rate? You take your antiderivative. You got to be careful with units here, and I did this very intentionally. Okay? Notice this is in acres per hour. This is in hours. So the way to get to acres, which is what we're looking for, is to take the antiderivative of 8 root t. Now, what do we put here? Notice I asked 1 day later, but time is given in hours. So we're going to actually evaluate that from 0 to 24. So I did this intentionally to say, hey, pay attention to units. Okay? So, can we compute this? You bet. How do we do it? Well, first we take our antiderivative. You add 1 to your exponent and then divide by that value. So we have 16 thirds t to the 3 halves, and we evaluate that from 0 to 24. And now what we do is we evaluate the function at 24, subtract off what we get when we evaluate it at 0. So I have 16 thirds times 24 to the 3 halves power minus 0, which always makes me smile. And what do we get? Let me compute it so we all have our curiosity satisfied. And what we get is 627. Now, this is not my final answer, I claim. What did we find? What we found is that's how much it grew in the first day. But that's not what they asked. They asked how many acres are covered 1 day later. You can't forget your initial value of 2,000. So, this is our final answer. I don't know why I'm spelling that wrong. Okay? All right. One more example here. Suppose I tell you this. Water is pumped out of a holding tank at a rate of 5 minus 5 e to the negative 0.12 t, and that's in liters per minute. Hence, t, our units are minutes. And what we're given is that it initially held 1,000 liters of water and when the pump started, and we want to know how much water does it can hold 1 hour later. How much does it hold after 1 hour? This is another one where we've got to pay attention to our units. All right. All right then, so notice we're given the rate in liters per minute. We want to know liters. Again, the way we undo our rate is precisely by taking our antiderivative. So we're taking the antiderivative of our function. Notice when we do that, this is in liters per minute, this is in minutes, we're going to get liters. So We want to know after 1 hour. Well, we're kind of keyed in on the units, and we know an hour is 60 minutes. So what do? We take our antiderivative. The antiderivative of 5 is 5t. And the antiderivative of 5e to the negative 0.12t is 5e to the negative 0.12t divided by negative 0.12. And we evaluate that from 0 to 60. Now, because we're dealing with an exponential function, we know that we cannot ignore our 0. So what do we get? Well, we're going to plug in 60 and then subtract off what we get when we plug in 0. Well, if we plug in 60, we have 5 times 60. Notice I'm going to be using my calculator here anyway. The only thing I'm going to do is simplify that that's a positive. So plus 5 over 0.12 e to the negative 0.12 times 60. And then we need to subtract off, well, 5 times 0 is 0. But we still have 5 over 0.12 e to the 0 power. And when we compute that, we will get minus 5 divided by 0.12. We're going to get, I'm just going to round to the nearest liter, 258 liters. Question is, are we done? What did we just find? What we just found is the number of liters that was pumped out in the first hour. Is that what we wanted to know? And the answer is no. Okay, we started out with 1,000 liters. We've pumped out 258 liters. So then what are we left with? Well, 1,000 minus 258, which I could have done in my head, is about 742 liters. And that's how much remains in the tank. Now, another way that we can look at this is in terms of looking at things like marginal cost and our cost function. So I'd like to do an example of that. Okay, when we talk about marginal cost, it's the rate of change of your cost function. So for example, if I have C of Q is my cost function, that's the cost to produce Q items. When we talk about the marginal cost, that's precisely the derivative of our cost function. And what does the marginal cost mean? It's the rate of change of your cost with respect to quantity. Something else I want to point out, going back to my original cost function, is C of 0. Those stand for our fixed costs, okay? No matter what, there's always fixed costs. If you own your building, taxes are a fixed cost. If you rent your building, rent is a fixed cost. There's just the basics of electricity, payroll, insurance for your employees. All of those sorts of things lend themselves to fixed costs. Then what you have is the cost to produce each item, okay? Those are your marginal costs. So, what does it mean then to look at this integral? Okay, well, clearly we're going to get back to our cost function, and again, let's look at the units here. Okay, this is cost per item. This is the number of items. So we certainly get our cost function back. And essentially what we have here is the cost to increase production from A units to B units. So what if we wanted to know, if we knew our marginal cost, what the cost is to produce B units? Well, what we would come up with, the total cost to produce B units, well, in words, we're going to have our fixed costs, and then what we're going to have are our variable costs. Okay? In other words, the cost to go from making 0 units to B units. And where do we get that? Well, our fixed costs are C of 0, and the variable cost is the definite integral from 0 to B of our marginal cost function. Okay? So what does this look like then in practice? Well, let's take an example. Suppose I tell you that the marginal cost of a product in dollars per unit is given as this. C prime of Q is Q squared minus 50Q plus 700. And suppose I tell you that the fixed costs are $500. And I want us to find the total cost to produce, let's just say 50 items. Well, if I asked you what is the marginal cost function, this is what you're going to tell me, okay? So if I want to find the cost to produce 50 units, what I have to do is take my fixed costs, 500, plus, well, now I need to know what is the cost, the total variable cost to produce 50 items. It's the definite integral from 0 to 50 of our marginal cost function. Is that something we can compute? You bet, okay? I'm going to bring this 500 down at the end. Right now what I'm going to do is focus on my integral. So we get Q cubed over 3 minus 50Q squared over 2 plus 700Q. And we'll evaluate that from 0 to 50. Notice we have a polynomial, which is sweet because plugging in 0 is a moot point. So really what we need to compute is, we got this 500 we're bringing down, plus, well, 50 cubed over 3. I'm going to simplify that, minus 25 times 50 squared, plus 700 times 50. And not that we really care too much about what the answer is, but let's compute it just so we're all on the same sheet of music. Here, divided by 3 minus 25 times 50 squared plus 700 times 50. And we get $14,666.67. So there's another way to look at the applications of our definite integral. All right, thank you.